Hello. Alright, we're gonna try out light background music this time. Let's get going. Number 171, Excel sheet column number, easy. No, we already did this. No, we didn't do this. We did it the other way around. Given a string column title that represents the column title as appears in an Excel sheet, return its corresponding column number. For example, A goes to 1, B goes to 2, C goes to 3, etc. Z goes to 26, AA goes to 27, AB goes to 28. Okay. So this is the same as last one, or it's the inverse of the last one, but this one will be a lot easier because there's no modular arithmetic to do. You just iterate backwards through the string. So for character in column title backwards. This alien face operator means from start to end because I didn't put in the ranges, and then by -1, which means it goes, it iterates over -1 characters each time, which just means goes backwards. So for the characters in reverse order, let's store our return value started at 0. For each character, we want to convert it from a letter to a number. So let's open up Python and remind ourselves how to do this. I know there's ORD and CHR in Python. So ORD of capital A is 65, which just means we want to subtract 64 from whatever ORD of C is, because we want A to be 1. So you take ORD of this, minus 64, you add this to ret, and you return ret. But then we just have to make sure that each subsequent one adds an extra 26. Because when you're the second A, you're 26 instead of 1. You add 26 instead of 1. So we just need to remember the characters for I, this, or remember the index in enumerate. And then this is times I times 26, right? Oh, but this I should start at 1. Can I just do enumerate starting at 1? Or is that the second argument to enumerate? So maybe I don't want to start at 1. I'm getting numbers that are too big. So I'm guessing the reason I'm getting 0 is because I starts at 0. Oh, I want this to be 1 on the first one, and then 26 on the second one. So this is not the right way to do it. What I want to do is 26 to the power of I. There we go. So I multiply it by 26 as many times as we are I. So submit that. There we go. Beats 100%. Pretty good. Yeah, there's no real way to improve this. So let's move on. Number 172, factorial trailing zeros. Medium. Given an integer n, return the number of trailing zeros in n factorial. Note that n factorial equals n times n minus 1 times n minus 2 times etc. times 3 times 2 times 1. Follow-up, could you write a solution that works in logarithmic time complexity? Alright, well why don't we start by doing something that works at all. The number of trailing zeros. So the most obvious way to do this is to calculate out the product and then count the zeros. And I'm guessing that's going to be too slow. I don't immediately have any insights into what would cause there to be zeros so that we can skip the calculating part. I guess every time you multiply by 10, that adds a 0. Yeah, I guess I don't know. I don't know how to directly count the zeros. So if I add a test case that's like 15, and I just want to see what it expects for that. Expected 3. I guess I do want to see, so for I in range n, ret equals 1, ret times equals n minus I. Return ret. So obviously I'm not returning the right thing, but I just want to see. So this is the factorial number. Then I could just count the numbers on the end, the zeros on the end. And then I guess the trick after that would just be how many times can you divide this by 10 with no remainder? But I guess I still don't see how to do that without doing the multiplication. So you could take a look at the product, and some of the products will be divisible by 10. So you could take a look at those, and those would give you some of them. But some of them won't be, like 2. If you do 5, then the 2 and the 5 together give you 10. Although I guess you're always multiplying integers. So the only way to get a number divisible by 10 is if one of the factors in the product is a multiple of 10, or 2 and 5 and those are the only two cases. So for 15, no, because how do you get 3 zeros here? Because I would have said 2 times 5, that's one of them. 10, that's the other. How do you get the third 0? So 15 equals, or 15 factorial equals 15 times 14 times 13 times 12 times 11 times 10, 9, 8, 7. I'm taking so long to write this. Let's just say equals like this. Three, 2, 1. And I was saying here's one of them, and then if you combine this and this, that's another one. What else makes this divisible by 10? Because the rest of this needs to be divisible by 10, right? Let's open up Python. Excuse me. So you've got 15 times 14 times 13 times 12 times 10, 11 times 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that has 3 trailing zeros. Now if I divide this by 10, I can remove the, well, I don't need the 1, and then I can remove the 2 and the 5 together, and this should give me 1 fewer 0. Yes. Then if I remove the 10, I should have 1 fewer 0 again. Okay. Now where's the last 0 coming from? Or is that not the right way to think of this? Nothing else in here is divisible by 10. There might be some pairs that are divisible by 10, like what's 15 times 14? That's 210. But 15 times 12 is also divisible by 10. Are there any other pairs? Well, I can't do 10, obviously. I guess there probably aren't any other pairs. So the 15 times sum of the stuff is also divisible by 10. So would I just have to find every pair, check if it's divisible by, if its product is divisible by 10? And if it is, take it out of the list and put, like I would put 21 back in the list instead of 15 and 14, and then check if 21 times anything else is divisible by 10. Or maybe I could take the other thing I'm thinking is we take the product, like we actually go through the number and we take the product. Every time it's divisible by 10, we divide it by 10, and then we keep going. But aren't we gonna end up with huge numbers? I guess I don't actually know what the challenge of the question is. Oh, no, I do, because it says here, could you write a solution that works in logarithmic time complexity? Logarithmic in the size of what? The size of n? Because I guess right now what we're doing is exponential. No. It's linear. You get one more step when you have n be one bigger. To make it logarithmic, I would have to not look at every factor. Yeah, I guess the problem is I have to have a way to know which factors are going to be contributing, right? Otherwise I can't skip over the non-contributing factors. Works in logarithmic time complexity. Well, maybe we need to do our easier solution first, just to get our, just to get my brain working, thinking about the relevant aspects of the problem. So the easier solution is you go through the factors, you do this product, you remember the result, and then you multiply the next thing by the result, and every time that you can divide by 10, you do divide by 10. We're still going to end up with a huge number. I don't know what we're going to learn, if anything. But let's try it. So count equals 0. This is not actually ret. This is product equals 1. Product times equals this. If product mod 10 is 0, then divide it by 10. You can do integer division. It won't matter. And increase our count. Then return the count. So give the, yeah, okay. This gives the right answer. And it's relatively fast, but it's not logarithmic. So if I had a test case that was very big, how big do they say the test cases can get? 10 to the 4, so it can get up to 10,000. That should be slow, right? Wait, I didn't add the test case. How do you add the test case? Or I did add the test case and it was not slow. So I guess this is gonna work for submitting the answer, but it's not the solution that they're hinting at. No, it did exceed the time limit. Okay. Even though it was less than 100 milliseconds? I guess they can put the time limit as whatever they want. Okay, so we get to figure out the logarithmic thing. If I use the test case, will it run? Or will it say... That's so weird that there's a difference between the submission and the test cases. Anyway, logarithmic time complexity. That's gonna mean you don't look at every factor. Okay. Well, I guess I'm still thinking it's got to be something like... Because look at this, it wants thousands of zeros in the N9000 case. Let's revert this test case back to being 1. Like, why does 15 times 14 give a multiple of 10? Fifteen times 14 is the same as 21 times 10. 15 times 12 is the same as 18 times 10. But how could you know? How do you know that without having to go through all of the factors? It was 12, what was the first one? 12, 15 times 12. For example, it's not the only one. So these are my factors of 10 for 15. I mean, you can't look at every pair because that's going to give you n squared runtime. Interestingly though, it would give you O of 1 extra space. Because you would only have to keep a count. You would never have to keep any extra data, like what the actual products of stuff are. But there's got to be a way to only look for specific values. The fact that it's log of n is interesting. Especially since, well, I don't know. I don't know if the log is coming from the fact that we have to do log of n steps, or if it's just coming from the fact that the size of the output is going to be log of n, because it's a number that can be represented with n bits. I don't think Leetcode usually counts that though. I think they would usually count that as O of 1. I'm not sure. Yeah, not sure how to make progress here. My only alternate idea other than go through and take the product, which is linear time, is go through every pair and pop out the ones that are factors of 10. Or yeah, multiples of 10. I must be missing something. Well, I am obviously missing something, but I must be missing something about how to recognize these. Because if well, you know what is jumping out at me right now? 15 and 12 is each of those is 10 more than 2 and 5. Huh. So maybe it's something like every factor that ends in 0 is going to contribute, and every factor that ends in 5 is going to contribute, because that's going to, a factor that ends with 5 is going to come after a factor that ends with 2. So together the 5s and the 2s contribute. So so you really just want to know how many numbers end with 0 or 5 in your list of products. Is that possibly the case? So without making it fast yet, I just want to know if that could possibly be it. So let's still go through our list of products. Term. Factor. We don't need the full product. We just want to know if another way to say ends with 0 or 5 is that mod 5 equals 0. So count plus equals that. Does that give the same answer? Almost. It gave the same answer on the small test cases. It's pretty far on the very big test case. So let's find a test case slightly bigger than the ones we're using where it fails, like 21. Wait, why did it work that time? Oh, because I changed the existing test case. Wait, I still want a test case with a really big number. Okay, so what's some small number where it'll fail so I can actually try to trace it? 27. So I would say there's 5 for 27 because there's 5, 10, 15, 20, 25, which is 5. But there's actually 6. Um, okay, so it's not this simple. Oh, wait. The even numbers can also create multiples of 10 once you have 5 of them. So for every 5 even numbers, it's not every 5 even numbers, it's every 5 multiples of 2. But I'm using some of the multiples of 2 to multiply my 5s. But I should count the rest of them. And when I get 5 of those, I get a multiple of 10. So like, this is hard to explain, but like, is it even true? So that would mean 4 times 4 times 4 times 4 times 4 is a multiple of 10. Is that even true? It's not true. But 2 times 2 times 2 times 2 times 2 is. No, 2 plus 2 plus 2 plus 2 is, not times 2. Where's this extra 0 coming from? There's some other way, and it's going to be starting at 27. I don't want to write all those numbers out. I don't know if that's going to tell me anything. So this first 2 and this 5, when you multiply this 2 and this 5 together, you get 10. If you divide that out of the product, then these go away. This 10 goes away also. This 12 and this 15 don't go away. When you multiply them together, you get 210. Which, when you divide the 10 out of that, leaves you with 21. Hold on, so the other thing that I said is contributing is 25 times 15, but that's not, or no, 25 times 22. Okay, that is a product of 10, but that one's a 55, which means it's also another product of 5. which means when you multiply this by like one of my even numbers, so 4, you get another 0. So I have to check if this is a multiple of 5, that contributes to the count. If it's a if it times 12 is a multiple of 5, or times the number that ends with 2 is a multiple of 5, which can only happen if it is a multiple of 5, because at 25 times 22, 22 is not a multiple of 5. Multiplying it by anything can't make that product be a multiple of 5. So what I want to do actually is continually mod this by 5 and keep counting as many times as you can mod it by 5. So term equals this. Factor equals that. While factor mod 5 equals 0. Count plus equals 1. Factor divide u by 5. Okay. Now I get all the right answers. This is so interesting. I'm surprised I was able to get this far. I'm pretty sure I found the important insight at this point. So now we just need to figure out how to skip to the right numbers. Like, we don't have to do all of these. We can just know that they're there based on how big n is. So how do you do that? How do you do that? Well, I'm already at 0 milliseconds, so I think if I submit this, I'll succeed. Yeah. But why is this logarithmic time, if it even is? Is this variance or... No, I think I still have some room to improve. I don't think this is logarithmic time yet. I think this is technically linear time. So one obvious quick improvement is I can start at 5 and we can skip ahead by 5. Then I'm never considering numbers that aren't multiples of 5. Is that how you do that? Print list of range 5, 25, 5. Yeah, that is how you do that. We're not including n, but we should be including n. So n plus 1 here. That made it have an infinite loop? How? What if I'm just printing this just to see what it gives? 5, 10, 15, 20, 25. That's what I want. Start at 5, jump by 5. Why doesn't this work? Time limit exceeded for n equals 5, and it didn't even print. What does it look like for n equals 5? It should just be 5. Oh wait, this while loop will go forever. Why wasn't that already happening? Well, for one thing, I don't want to... So I guess that this would happen whenever my n is equal to 5. So I could just say if n equals 5, return 0. If n... or actually you return 1, right? If n is 5. No. Hold on, I'm getting confused. Why would this be an infinite loop? Once you divide out 5, you have 1, and that's not mod 5 anymore. I mean, I still have the problem that I is starting at 5 even when when n is less than 5. Like, I think I just want to abandon the for loop and just do while I is less than n, do this, and then just I plus equals 5, because we don't need to check. We can jump by 5s. I needs to start at at 5. Or it can't start at 0. It has to start on a multiple of 5, but now if it's less than, if I guess I have an edge case here. If n is less than 5, return 0. Less than or equal to n. Come on! We had it before. How are we getting infinite loops now? Also, factor can just be I, right? Because we're just starting at... Oh, okay. Maybe it's because of the edge case of how we were iterating backwards. Or the boundary conditions were different than what I thought they were because I'm iterating backwards instead of forwards. Okay, this is only 5 times faster. It's not going to make it logarithmic. But that's probably going to put me at the left side, yeah. Oh, no, actually, I still only beat... I mean, this graph makes no sense. 80% used 57 milliseconds, and I used half of that, and I only beat 26%. I guess it's because it buckets them all together in the graph. Anyway, we can do better because we're still iterating over n numbers. We're just iterating over n divided by 5 numbers. I think what we can do here is just take the largest multiple of 5 and count all the others, if that makes sense. Like while we're finding how many factors of 5 are in 15, we're also finding, we know that every factor of 5 that's in 15 was one of the other numbers in our term, because every number smaller than 15 is in our term. Right. Right. How do we... How do we account for that? Well, I guess like every time we go up by 5, we could count one more for each factor that we find. And that would count the previous ones. So then if we start with only the largest product of 5, is this making any sense? So I'm trying to say, like, you've got 25, so 15, 10, 5. So for all the numbers between 25 and 29, the answer is going to be 6. And the reason is you count all of the factors of 5 in here, and you've got 1, 2, 3, 4, and then for 25 it's 5, 6. So if I looked only at 25, basically if I divide 25 by 5, that's how many factors of 5 came before me. Right? That's how many factors of 5 came before me. So then you could count 25 once and all of the factors once. That would give you the answer immediately. Well, except that you also have to count the factors within the factors. So in this case, this one should count twice because it's got 2 factors of 5. And then when you divide 25, so 25 divided by 5 equals number of factors of 5 that came before. Or that including the ones that come before. So you just divide by 5 and you get this. You get 1 count. Yeah. So I'm picturing like a pyramid pretty much. Where so 25 is here. It counts twice, and it can count all of the ones that came before it also. Then 30 is going to be the next one, where it includes, where you can do the division thing to get the count of these, but then you also have to figure out how many of them count twice. How do you figure that out? It's like, I'm so close here. It's like, so you take the division to get the number of them, and then you have to see how many count twice, which is the number that are greater than 25. Which would be these. So for 35 it would be 3, for 30 it would be 2, for 25 it would be 1. How do you figure that out immediately? Actually, is that even true? Does it really look like a pyramid like that? Because you have 25, if you divide that by 5, you get an extra factor of 5. If you have 30, that's not an extra factor of 5. So when is something going to count twice? Whenever this becomes a factor of 5. So every multiple of 25 will count twice. So I don't know if it really looks like a pyramid like this. So if I take n divided by 5, that's the number of factors of 5 in the product. And then I want the ones that count twice, which would be n divided by 25, number of factors of 25. And then I keep going. N divided by 125. Okay. This might be it. So now there's no, okay, I guess there still is some iterating. You just go count equals 0. I want to bring this up here so I can look at it. N over 5, so count plus equals this. Then you want to keep doing that. So while count mod 5, it's not while n is greater than 1, let's say, you do this and you divide n by 5. Amazing. 0 milliseconds. We did it. What a crazy algorithm in the end. Yeah. Usually the math ones are really hard to figure out unless you kind of already know the trick. But in this case, we derived the trick by looking at the factors, seeing which pairs gave a product of 10, and then finding faster and faster ways to calculate how many products of 10 you're going to have in there. Very cool. Next problem. Number 173, binary search tree iterator, medium. Implement the binary search tree iterator class, BST iterator class, that represents an iterator over the in-order traversal of a binary search tree, BST. BST iterator tree node root initializes an object of the BST iterator class. The root of the BST is given as part of the constructor. The pointer should be initialized to a non-existent number smaller than any element in the BST. Boolean has next returns true if there exists a number in the traversal to the right of the pointer, otherwise returns false. Int next moves the pointer to the right, then returns the number at the pointer. Notice that by initializing the pointer to a non-existent smallest number, the first call to next will return the smallest element in the BST. You may assume that next calls will always be valid. That is, there will be at least a next number in the in-order traversal when next is called. Okay. So in this example, you're going to return 3, 7, 9, 15, and 20. 3, 7, 9, 15, and 20. And then has next just obviously returns whether or not there's something left in the list. Okay. So there's a way to kind of cheat in Python here, which is to use an iterator, like a built-in Python iterator. So we could do a recursive traversal of the tree, and then just yield from the tree, from the iterator. And then whenever you call next, you call next on our iterator. Has next would be a little trickier, but could figure out a way to fit it in there. But anyway, I think that probably goes against the spirit of the problem, because it's just hiding the state saving code into Python built-in language features. So we're gonna figure out how to do this without using a Python iterator. So we kind of, whenever we do next, we kind of want to manually do a tree traversal. So at any given moment, we want to remember what node were we on. We have to remember the path that we took to get here, so that we can go back up, because the tree doesn't have like pointers back up. And then we either go left or right or up, depending on what our state was. So I think our state needs to have a stack. Self.stack equals this, and you can start with root. Every time we go down, we have to add to the stack. Every time we go up, we have to pop from the stack. We also have to remember, so in order means you go left, and then you go to yourself, and then you go right. So we have to remember what we've done so far. So, oops, self.state equals we're going to start by saying we need to go left. So I guess when the first thing you're supposed to yield, return 3, would be the leftmost thing. So when we initialize the tree, how do I say this? Like every time actually, I'm not sure how simple this is. I was gonna say every time we want to go left, we go all the way left. We recurse all the way down as far left as we can, and then we yield that node. At that point, we have to say the state I guess we're never gonna say the state is middle is like myself. It's always going to be either left or right. Because I guess if we were doing a regular in-order traversal, it would look like this. Traverse, route. You would do like visit, route, between doing traverse route.left and traverse route.right, right? So how do you turn this into a non-recursive thing? The stack thing I think is right. That's how you remember where you came from, and then you push to the stack when you go down and you pop from the stack when you go up. I'm just having trouble visualizing, like, when I do next, how do I remember the state? I'm just gonna do something that I think doesn't work just to see. Has next is gonna be simple. It's just going to be return bool self.stack of -1. So if I have, or yeah, just self.stack. If there's no stack anymore, then we're done. Then the thing for next is you kind of want to do like this, right? Where it's like, depending on what our current state is, we're either going to go left or visit ourselves or go right. The problem is this is we don't get called this much. We only get called, we want to yield whenever we visit. We want to do all the traversing stuff before yielding. Which means that anytime we have yielded, so anytime we return from next, we want to do like ret equals this, return ret. And what are we actually returning? The value? Returns the value, so return ret.val. So at any given point, like let's say we are here, that means we've already visited the left and now we have to visit the right. Right? So it means you're always either going right or up. No, because you have to go left sometimes. I guess after you go up, so let's say we've just yielded 9. Now we have to yield 15. So after going up, you yield yourself. Oh, I can't believe how confused I'm getting here. After yielding 9, you go up and you wait. After yielding 15, you go right and you wait. After yielding 20, you're done. Okay, after yielding 3, you go up and you wait. Then the next one, we're gonna say next, and we're gonna yield 7, and then go right. And then go left. We always go as far left as we can. And then after yielding a left, we go up. And then we yield the node up. This should not be this hard to think through. Because you start by going as far left as you can. And then you yield this. So I can either have it so that when I call next, I'm on the node that I want to return, and then I have to go to the next one, or I'm on the previous node and I have to get to the node I want to return. Let's say that I'm on the node I want to return, always. So when you initialize, that would mean you have to do while self.stack of -1 dot left. Self.stack.append self.stack. Here, I can do this. Walrus operator to assign a variable while you check if it's true. So this will start my stack and myself all the way down in the left. State, I'm not sure how this works yet. Then anytime you call next, you start by getting the node that we're on, so the last thing in the stack, .val. And now we navigate to the next thing we want to go to. Which means you go up by 1 if your parent is on the right side. need a bigger tree than this. I'm not... I'm not picturing the edge cases properly. I'm just gonna imagine that 3 has branches on the left and right. So you would start by returning whatever's in the bottom left of the tree. Then you go up by 1 and you wait. Then the next time we call next, we return this. Then you go right. And anytime you go right, you then go all the way left afterwards. So we either go up 1 or we go right. Then full left. Those are the 2 choices, right? You go... Because after 7, you would give 9. Is that right? Yes. Okay, so every time you go right, you then fully dive left. Anytime you go up, you stay there. How do we decide if you go up or right? That's the last remaining question. You go right if you've already gone left. Because we did 3 and then we went up. We don't have an up from here, but let's imagine we did. So we've got a 1 and a 2 over here. So we start with 1 and then we go up. Now we want to go right, and the reason is we've been left. So for each node we need to remember, have you been left or not? So for each node, we also need to remember, have you been left? So we'll say false. Well, or don't we want to say true, starting from the root and going down left? So as we're appending stuff, how do I say this? It's like we haven't been left yet. No, these should all be true on the way down left, because then we have been left on all of these. Then when you do next, you can't just take the val here, you have to pop this, and you're going to end up with node and then left. So at the end we return node.val, and then we decide if we go up or right. So if then left, then we go up. Which basically means you don't do anything, because go up hold on. So if we're like here, then we've popped this, we've said we've gone left. No, we've always gone left. Wait. We've always gone left. The question is, have we gone right? No. So you go down to this, and then you go up. Then you've gone left, but you're trying to decide, do you go right or do you go up? And you'll always have gone left. So what we need to know is, have you been right, actually? If you've been right, then you go up. This should just be called been right, and these should start as false. Okay, if you've been right, that means you go up, and since we've already popped you out of the stack, that means there's... I was gonna say there's nothing else to do. I will continue to say there's nothing else to do. That's right, there's nothing else to do because we've already popped you from the stack. Else, so you have not been right. Now we have to add myself back into the stack. So self.stack.append node, but we can say that we've been right this time, or true. Then every time you go right, you want to dive left all the way. So we do this again. Okay. Yeah, this is the 0th thing. Yes, because I just want to pop from the stack. This is the 0th. Alright, well, we didn't crash, but we're not correctly traversing the tree. Null, I think, is when you're just initiating the binary search tree iterator. 3, we did return the right first element. Then we said 3 again, which is not right. So the first next, then right should be false. So we should go into the else. In the else, we put ourselves back in the stack. Wait. Because we start all the way, well, I guess in this example, we start on 3. So we're going to return 3. And then we're going to say we have not been right. And then we're going to try to go right. I guess the problem is we can't go right, so we should still go up by 1. So if you've been right or you don't have a right. Okay. I think I'm gonna need to print self.stack at the beginning of each next call. Okay, so we get pretty far. Can we also print node.val as we go so I can see what we've output so far? So we start with 3 and then 7 and then 3 again and then 7 again. So how did we get back to 3? So the stack, I also want to print the stack is also hard to read. Let me print n.val and then the Boolean thing for nb in stack. So we start by saying 7 and we haven't gone right, 3 and we haven't gone right. Then the first time you call next, we return 3. And now we're back at 7 and we have not gone right. Then we return 7. Now we should be going right. Oh, I never did the going right part. I only did the going left part. So you append yourself back in and then you go right. So self.stack.append node.right. And this one you have not gone right on. Okay, we're making progress. So now we did 3, 7. Oh, actually the only problem left is that we think there's still stuff to do at the end. So we said we never went right on 20. So we think there's still something to do, and we're going to find out once we try to go next that there's nothing to do. So can we fix that by how do we fix that? I also yeah, how do we fix that? So like one way is we could not say true, or we could not say false if there is no right. We could just say you've been right if you don't have a right. So every time that we're adding a node, we could just do def add self tree node. Are they called tree nodes? Yeah. Node, which is a tree node. Looks like this. And then instead of just saying false, you say node dot right is not what do I want to say? If so, and then sometimes I want to add true. So add Ben right is a bool. So I want to do this, but only if node.right. So Ben right and node.right. Is not none. Then I can replace all of these with and I can do equals false. Self dot add left. Add left true. Wait. A node true. This one is node.right false. This one is left. Let's go back to printing our stack. Print node.val or just n.val comma b for nb in self.stack. No, actually, I want to say or it is none, because I want that to be true at the end. Okay, so at the end, we know that we've been right everywhere. If you've been right everywhere, then there is no has next. But what's going on here? Why didn't we end up going up or anything? Because Ben right would be after we've yielded 20. Let's go back to print node.val. So after we yield 20, what does our stack look like? Print here, just this whole thing. We only went up by 1. So what we could do here is just say if return all of self.stack like bin right, so it's b for nb in self.stack. or return, that would be when there's not a has next, so not all. No, that doesn't work either because because the 20, or okay, I'm just gonna cheat. And the way I'm gonna cheat is I'm just gonna check if we ended on 20. So what does our stack look like at the end? It looks like, did I print this? It thinks we're on 15 because it thinks we've been right on 20. We can detect that though. It's like if you have been right, so if we go up 1, but we've already been right on the one that we went up to, then we're done. If we've just gone up 1, but we've already been right on the one we just went up to, we're done. So that would just be return self.stack of -1, 1. That happens after 9. Oh, I guess it's at this point we're no, wait, why does that happen? So at 9, the stack looks like this. 7, we have been right. 15, we have not been right. 9, we have been right because it doesn't have a right. So then you return this and you go up because this is true. So now you're on this, and that is what we're on. So now we're on 15 and we have not been right. And then I guess here I would say, how can I tell the difference between we're on 15 and we haven't been right, and we're on 20? No. If we're on 15 and we haven't been right, then this should... No, I guess the last thing could be either true or false. This doesn't make sense. What did I want to say? I want to say if my... How can you tell that you're done? It's if you're... We can just cheat and say if the last thing you did was the rightmost thing, then we have to figure out the rightmost thing, and we have to keep track of the last thing we did. I'm trying to see if we can just like look at the stack and tell that we're done. So at the end here, we should have been right. But on our parent, we should have also been right. It can't just be that though, right? Well, isn't this what I was doing before when I said if you've been right on everything? Turn not all be in for node boolean in this. In stack. We've been right on everything before we do number 20, because I'm counting been right when the value is none, or when there is no right. What if I just don't do that? Then it works. Okay. Okay, now the question had some extra constraints here. Follow-up. Could you implement next and has next to run in average O of 1 time and use O of H memory where H is the height of the tree? Well, I'm already doing the O of H memory because I'm only remembering a stack that goes up to the depth of the tree. Next and has next to run in average O of 1 time. So next either is O of 1 because either we just go up by 1, which is O of 1, or we go all the way left. This is an average of this is an average of O of 1. Because if ever we go all the way down left, we don't have to redo that. So for every node, we will add it to the stack twice. Once with a true, once with a false. Like at most twice. Which means that as you go through all of your nexts, there's an average of 2 per next call. which means it's there's an average of 2 things added to the stack per next call, which means it's O of 1 on average. Worst case, you could go O of H, but on average it's O of 1. And then has next, I'm going through the whole stack. And half of the time, at least, the stack will be of height H. So this is not average O1, this is average O of H. This could be made to be exactly O1 by doing the thing that I was saying was cheating, which is to just self.last element equals root, and then do this. While you can go right, self.last element. Oh, not like that though. While self.last element has a right, then keep changing it. Then over here I can just say return self.stack of -1 equals self.last element. Though we're not actually ending on the last element, right? Because after you pop it, we're either going to go up by 1 we are going to go up by 1 because we don't have a node.write. So I guess I want the before last element. No, we can just do last element. We can just remember self.is done equals false. Whenever you visit the last element, if node equals self.last element, self.is done equals true. Here you just return self.is done. Right? Not right. Oh, return not that. Yeah, okay. Okay. Then so this is O1 obviously. This is still O1 on average. What was the last thing I wanted to do? Like, we don't need this thing anymore. We just do self.stack.append left and false. Where else am I doing add? So node and true. Node.write and what was it? Yeah, node.write and false. Left and false. Okay. Yeah, and it didn't say what the initialization cost should be, so my initialization cost is O of H. Obviously you can replace this if nothing and then else with a if the opposite. So if not then right and node dot right, then you do this stuff. Okay. Okay, cool. Oh, wait. Wrong answer. Oh, this doesn't need to exist here. Interesting. Okay, I thought we had figured this out. Use test case. I wish we could visualize the test case. This is some tree traversal, right? How does it... I went back to 1 somehow. How does it provide the tree? Does it say that? How do I picture this? Well, okay, I guess I don't have to picture this version. I can just, I know that this is a pre-order traversal. So, so let's see if we can try to draw the tree. It's like 1 is the root, or no, 1 would not be the root. Wait, this is hard to do without the nulls. Is it something like this? 1 on this side, 4 on this side, nothing on this side, and then 2 on this side? No, because then we would return 1, 3, 4, 2. So it must be that 2, 3, and 4 are something like this. Because then we would return 1, 2, 3, 4. But it's starting with 3 here. Which would be weird if 3 is just in the middle here. So is 3 the root? And then you've got 2. if the 2 were on this side. I don't know. How do I read this input? Why can't I just see what the stupid tree looks like that I'm trying to parse? It doesn't say what the order of that tree is, right? It just doesn't explain how to read this input. I guess I can figure it out from the example. So this example is 7, 3, 15, null, null, 9, 20. So I guess it's reading it in order of the levels, kind of. So it's so in this example, it would be 3, 1, 4, null, 2, and then null, null. Okay. Which should give 1. And then we go right. And okay. Actually, I think no, I don't see the problem yet. Let's trace our code on this tree. So in case it's not obvious, the links look like this. So let's go back to printing the stack. I have to keep writing this code because I keep thinking I'm done. B for node B in self.stack. It's not B that I want actually, I want the pair n.val and B. Okay, so on this tree, we start here. We're going to output 1. Let's also print node.val. So we start here, we output 1. Then we go right and then all the way left, which leaves us right here, and we output 2. Then we go up. We only went up 1. But we should go up again because we've been right. So I guess we want to keep popping up the stack when we go up. So this is the else. Go up. That means pop off the stack. Pop off until we have not been right. So while self.stack while the last thing in the stack, the 1 index is whether we've been right. So while we have not been right, or sorry, while we have been right, because we want to go until we have not been right, self.stack.pop. Do we end up popping everything at the end? Does that mean we can get rid of this and go back to self.stack? Return, yes, self.stack. Aha! Okay, so we don't need to remember the last element anymore. We don't need to remember is done. Okay. This is how I thought it would work, but I didn't think through that you'd have to... I thought that you would end up with no stack at the end, but I forgot to think through that you have to go up more than one level sometimes. Alright, remove our print statements and submit. Ta-da! Okay, pretty cool. Pretty cool. Next problem. Number 174, Dungeon Game Hard. The demons had captured the princess and imprisoned her in the bottom right corner of a dungeon. The dungeon consists of M by N rooms laid out in a 2D grid. Our valiant knight was initially positioned in the top left room and must fight his way through the dungeon, or through dungeon, to rescue the princess. The knight has an initial health point represented by a positive integer. If any point in his health drops, if at any point his health point drops to 0 or below, he dies immediately. Some of the rooms are guarded by demons, represented by negative integers, so the knight loses health upon entering these rooms. Other rooms are either empty, represented as 0, or contain magic orbs that increase the knight's health, represented by positive integers. To reach the princess as quickly as possible, the knight decides to move only rightward and downward in each step. Return the knight's minimum initial health so that he can rescue the princess. Note that any room can contain threats or power-ups, even the first room the knight enters and the bottom right room where the princess is imprisoned. Okay. This is a Advent of Code style puzzle, and it's also clearly a dynamic programming kind of puzzle. So they labeled it as hard. I think that's weird, because I think it's going to have an extremely straightforward dynamic programming solution. So the most health that you need to be in the bottom right corner is like the inverse of the value of the bottom right corner. So you need 5 to get to be -5. The most health that you need to be in the cell right before it would be whatever's the like best between the cell on the bottom and the cell on the right, because the knight can only move downwards and rightwards. It said that, right? So we just need a dynamic programming table. So table, we can call, I like calling it cache, equals it's like a 2D array. So you've got the effective value of each room, which is just going to be the sum of the best path towards the end from that room. I guess we'll start them at none. You shouldn't end up accessing stuff in the wrong order. So none times len of dungeon of 0 for blank in len of in range of len of dungeon. Let's just print that to make sure that's the right size. Yeah, that looks like the right size. Then we iterate from the bottom right up outwards. So for I in range len of dungeon for j in range, one of these needs to be of 0. Let's make j be that one so that we're indexing at ij. We need to go through these in reverse because we want to start in the bottom right. So reversed. At the end, we're just going to return negative cache of 0, 0. And then along the way, we just take the sum. So the sum is, well, okay. First, the bottom right cell, so cache of len, I'm just going to define m and n. M and n equals len of, and I'm going to do that first. Dungeon 0, len of dungeon. This is m. This is, or not without the len, so this is just m, and this is n. This is n, and this is m. Okay, easier to read. Oh, yes, the bottom right, so n m is going to be equal to dungeon of mn. So the value in the bottom right is the value of the dungeon at the bottom right. And then for each cell, its value is going to be whatever is best, which is to say highest, because we want the minimum health that you would need. So whatever is highest between these two. So cache of mn is equal to whatever's highest between this and this, the one to the right or the one below. Then we just need to make sure that these are real valid indexes. So if m is, wait, I've been confusing m, n, and I and j. So these should be I, my m's should be I, my n's should be j. And then this is if if I is less than n, minus 1, right? Because you can't index into n. So if it's this, otherwise, let's just say negative infinity. So from math import infinity. And then the same here. If j is less than m minus 1, else negative infinity. And that's it. Oh, these... Yeah, I've got a bunch of off by ones here. So I could do... What's the right way to do this? Maybe I'll just do minus 1, minus 1, minus 1, minus 1. I'm getting null. Why is that? Print cache. Everything's negative infinity. How did I pull that off? Wait, I've switched m into n here. This should be n, this should be m. They're the same number, so I don't... But everything is negative infinity, so my cache didn't even get a value here? Print cache. Yeah, it starts with -5 and then it gets replaced. Oh. Because I don't actually want to overwrite that one. If I equals n and j equals m, continue. N minus 1, m minus 1. Oh, and then I have to add the value of this dungeon cell too. Dungeon of I, j, plus that. Okay, we're getting closer. So you've got -5 in the bottom right. Directly left, you've got 25. Directly above, you've got -4. And that is correct. And directly left of that, you've got 35. Directly above that, you've got -1. And that's also correct. Oh, wait. I am not taking into account the fact that you shouldn't go below 0. Ever. Okay, how do I take that into account? So it's not enough to just sum. Let's instead keep track of the actual answer for how much health you would need. How much health you would need in the bottom right is negative this. If this is a positive number, then it's 0. So it's whatever's max between 0 and negative that. Then how much would you need to be here? No, not whatever's max between 0 and negative that. because then I lose. Yeah, whatever's max between 0 and negative that. Now, how much health would I need to get to this point? So it would be the value of this plus whichever is max between these two. And then the max of 0 and that. Wait. I'm getting confused between what HP does the knight need versus how much damage would they take if they went that way. Why don't we just say cash of IJ equals how much. That's the same thing. But let me just write it down so I can stop getting confused. If they went this way. Okay, how much damage would you take if you went here? It would be 5. If this were a 5 instead of a negative 5, it would be 0. You would take 0 damage. How much damage would you take if you went here? It would be 4. Because you add the 1 and then you subtract and then you add the damage that you would take to go to the other place. So it's value of the dungeon plus I guess you want the minimum in this case. We're saying 1. This is getting so hard to think about for some reason. How much damage would you take if you went this way? So you would heal 1 and then you would take 5. So you would take, if you went this way, you would take 1 less damage than whichever of these paths would give you the most damage. So my cached value here is a negative 5. No, my cached value is a 5. So I would take 5 damage. So here I subtract dungeon of wherever I am. And then I go whichever way would give me less damage. Okay. How much damage would I take to go if I went through this path? So I would take 10 damage. So that negate this and add it, plus whichever amount of these gives me the least damage. And that would be the left side, because the left side would give me negative 25 damage. Okay, and then at the end here I have how much damage would I take? Which is yeah, okay. The only thing I'm missing here is the maximum, the like cutoffs at 0. So how much damage would I take? If I went here, the answer is negative 25, as in I would heal 25. And then at the end, when you say how much HP would you need, you don't say negative 25, right? Do you? I don't know. Don't start these as negative infinity. If you're doing a minimum. Okay, I'm still not doing the cutoff at 0. I think that might be because this example doesn't have any or something. It's confusing me. How much damage would I take from here? The answer is negative 25. How much would I take from here? The answer is negative 35. But you don't take negative damage because it doesn't help you to bank up more than... Okay, so you don't want this to ever go negative. So this, you take the max of 0 and that. Okay, and then we just need to add 1 to the end because we're saying that you would we're saying that you would end up at the end with 0, but what we want is that you have more than 0. There we go. How do we go slightly left of the peak? There's a few things, like we're doing a lot of ifs inside the loop that we could take outside the loop. The whole bottom row and the whole right column could be calculated outside the loop, which would mean we don't need to do these ifs if we just started one earlier. And we wouldn't need to do this either. So let's do that. Optimization. Take the conditional stuff out of the loop. So basically, cache of I and j is set to the max, so m minus 1. Is going to be equal to, you know that you're not going to be doing this part of the min because there's nothing to the right. So so you can remove the min and just say plus this thing. And we can remove the if here if we just don't go all the way up to n minus 1. J would be m minus 1, j would be m minus 1. Don't go all the way up to n minus 1. So yeah, go one less high. And then we do the same thing for j. M to minus 1. This one starts at n is, yeah, this one starts at n minus 1. This one is j. This one is n minus 1. This one is j. N minus 1, j plus 1. So that means we don't need these conditionals. As long as we don't go all the way up to the last row and column, because we've already figured those ones out. And we don't need this either, because we're already not doing the last row and column. Submit. Okay, well, I mean, this is faster because we're doing less work, right? We're all of those conditionals that were in the n squared, we've gotten rid of at least n squared work. But yeah, I guess it's still variance of Leetcode for where you end up, exactly how many milliseconds it takes. Cool. Next problem. Reset the time. Number 175, combine two tables, easy. SQL schema, pandas schema. Okay, this is a new kind of question. I've never had a question that requires SQL as an answer instead of Python. Combine two tables. Column name type, person ID int, last name varchar, first name varchar. Person ID is the primary key, column with unique values for this table. This table contains information about the ID of some persons and their first and last names. Table address. Column name type, address ID, person ID, city, state. Address ID is the primary key. Each row of this table contains information about the city and state of one person with ID equals person ID. Write a solution to report the first name, last name, city, and state of each person in the person table. If the address of a person ID is not present in the address table, report null instead. Return the result table in any order. The result format is in the following example. Person table. This is just an example. Okay, so these are people addresses, and the output should be first name, last name, city, state. There's no address in the address table for person ID equals 1. That's why they ended up with a null. Okay, well this is easy if you know SQL. It's basically just select. The things we care about are address ID, person ID, city, and state. No. First name, last name, city, and state. So select first name, last name, city, and state from the tables are called person and address. Join address. It's highlighting stuff a little weird. I wonder if I'm supposed to have quotes around these. I actually can't remember Postgres syntax that well, but we'll see. Where, and then I just want to say address ID equals, or where person ID equals person ID, or what is it? What is the person ID called in the first? They're called the same thing in both tables. Okay, then I need to have names of these tables, so I'll call person P and address A, and then I'm going to say where a.personID equals p.personID. Person is the thing with the name, city and state is the thing with the address, and now I know this syntax is wrong. I just need something to tell me where my errors are so I can fix them, because I don't know Postgres SQL syntax that well. Syntax error at or near where. So it probably doesn't like these as things that I'm doing. Is it something like this instead? No? Do you just not have parentheses and you just do that? Nope. What if I don't have these? Okay, this is hard without looking up SQL, but if I look up SQL, I'm just gonna find the answer right away. I guess I don't know how else to make progress. What does this lead to? Oh. Yeah, that doesn't tell me. Like I know what I want to do. I just don't remember how to name the tables when you join them. like, yeah, I just have to look this up. So let's just Postgres syntax. Maybe the AI overview will probably be enough. Here, tell me how to do a join. It's a regular join. You can do table 1, comma, table 2. How do I name each table? From T1 cross join T2. Okay. Oh. No, how do I give them a name? Because or an alias or something, because I guess it's true that I could just okay, as alias. So it was as address as a, but my syntax for join might be wrong, but apparently you can just put commas. Or are these not the same types? Add person ID is an int in one table. It's an int in the other table. How do I how do I do a join with aliases? Because I also know that I want to do a left join. Because I want values even when there's no... I want all of the people even when they don't have an address. So I think I just have to see an example. From table, and then you can just do space and then the name of the alias. Left join, and then the thing on the right. But wasn't that what I was trying to do? Left join. From person as P, left join address as A. Oh, I think this might be the difference between actually, I'm not sure. Like, because there's also on. Is it the difference between where and on? Oh, you don't do equals equals, you just do equals, right? Yeah. And is where the same as on here? No. So where is a condition for what I'm returning, and on is a condition for the joining? How are you gonna do faster or slower? Is there really ways to optimize? No, okay, I ended up at the top of the peak by just running it again. Okay, really interesting. I didn't expect to have to be writing SQL. If these questions get harder, like if they're gonna give me more SQL questions, I'm really gonna be in trouble, and we're just gonna be reading SQL syntax as we try to solve them. But yeah, that's all for today. So hope this was helpful. If it was, please leave me a like on Leetcode and on YouTube. And that's all for now. Peace.